a standard theory that helps describe the functionality of columns, and it's referred to as plate theory. And then this has been modified and replaced in the last number of years by a probably more appropriate conceptual approach for trying to explain or understand how solutes or analytes are separated chromatographically, and that's referred to as the rate theory. Okay. When we're talking about these, we'll talk a little bit about how one actually can determine a parameter called the plate height, which is something that you'll be needing to do for your lab, for this lab. And that will lead us into talking about the Van Deemter equation, what that is, and a Van Deemter plot, which is also something you'll be doing for this lab. And then I have the quizzes to hand back. So don't get that again. Okay, so this is a part where we want to kind of get a sense of, how is it that people try to understand the process that's taking place, the chemical process taking place within a chromatographic column. And there's an enormous amount of, even though there's a theoretical framework to help understand this theoretical framework actually is utilized quite commonly in the development and modification of chromatographic procedures and the development of chromatographic columns to facilitate different kinds of separation. And on Friday, I'll talk a little bit about all the different kinds of chromatographic methods that are available and columns that are available, and I'll make a point on Friday of saying that for many companies, and there are probably at least a half a dozen companies that their major market is in the development and commercialization of chromatographic columns for a wide variety of uses. If you get on the internet, you'll find that in any given company, like Waters or Dynex, they have oftentimes well over 100 different kinds of chromatographic columns they've developed and that they market themselves. And these columns are, in some ways, are a very sophisticated version of like the inkjet printer ink cartridges. And that is, they cost a lot of money, they have a very limited finite lifespan, and they make a lot of money because they're expendable. And so these companies, they do pretty well developing and marketing these columns. And the basis for developing a column to achieve a particular chromatographic kind of separation is understanding what parameters in the column can be modified to optimize the ability to separate the analyte that you're interested in. That's what it boils down to. And in that comes the utility for understanding a theoretical construct for how separations occur. And that's where plate theory and rate theory constructs actually have some utility. So at the beginning, the plate theory concept sort of arose out of just basic liquid-liquid extraction separation schemes. And the idea is, we call it a plate theory, is that they're trying to describe a hypothetical construct. It doesn't actually exist, but describing a hypothetical construct that they're calling a plate. It doesn't exist. And this plate reflects the unit within the column of which the solute is interacting. This is going to facilitate the separation, either partitioning onto versus the mobile phase or coming off into the mobile phase. And it's that theoretical construct that is allowing the solutes to partition from the mobile phase onto the column components that are then facilitating the separation, because the different analytes in the solute will all partition with different affinities. We know that often. So they use this sort of plate theory construct that was developed first within framework of liquid-liquid extraction separations, and they applied it to column chromatographic separations. And it's a very similar kind of process, and it just really helps try to describe how things in the mobile phase will interact with the chemical aspects of the stationary phase to facilitate separation. So if we think of, this is your column, this is your chromatographic column. It's in input right now, and it has an input and it has an output. And we know that in the chromatographic column that you're using, that it's packed with beads that have on those beads conjugated quaternary ammonium groups that are then facilitating the interaction with the anions in your mobile phase And those anions will partition electrostatically or are attracted to those quaternary motives to different degrees. And it's the battle between the composition of the mobile phase and the composition of the stationary phase that determines the extent that the analyte partitions in one and the other and how strong they partition. Right? And so they take that reality of what a column is constructed of, and they sort of simplify it in this construct where rather than think of these tens of thousands of little beads that have this surface area with these functionalized group that's only the separation, they simplify it and they say, let's consider that the column actually contains these surfaces, and these surfaces that we'll define as these theoretical plates. And a plate is merely a hypothetical construct, and I want to emphasize this. This is a hypothetical construct. They don't actually exist. We know the composition of columns aren't filled with plates, but we can use this hypothetical construct to help understand how analytes are going to partition onto the column stationary phase, right, the mobile phase. Right? So I set all this stuff up here, right? The bottom line and what matters to you in understanding and adopting this, recognizing the importance of adopting this construct, is recognizing that the more theoretical plates that a column possesses, and you will calculate how many theoretical plates your column possesses. The more theoretical plates that a column possesses, that translates into a greater separation efficiency. And that's what matters, right? That's what developers of columns are striving to achieve, is greater efficiency of separation of analytes over a shorter amount of time. That's sort of the mindset. So if we want to measure these theoretical plates, it's actually quite simple to do. And some of you may have noticed on your printout, on the data printout for some of the data you're generating from the chromatograms, that there's several columns of data. And I think for one group of you, I was pointing some of those columns of data out that come out, that show up on the screen below the chromatogram. And one of those columns of data, I believe, is the theoretical plate height, or H. Right? And so if you look at the simple formula to calculate the number of theoretical plates, or the plate height, the height of each of those theoretical plates, and keep in mind, these are theoretical constructs, they're not physical entities, right? It's actually quite simple. So the number of plates in a column is going to determine, there's one parameter that's going to determine how efficient that column is at separating analytes, right, from one another. Right? And columns can possess a number of theoretical plates that can range from hundreds up to hundreds of thousands. And we know that the column efficiency, its ability to separate analytes, is going to increase with a greater number of theoretical plates. That makes sense, because it's like a unit upon which that partitioning is going to occur. And the more of those units we have, the greater we can facilitate the partitioning of analytes that have different partitioning coefficients on the plate or not. And the number of theoretical plates can be determined, and you will determine this directly from the chromatogram. We'll talk about that. But plate height, which is essentially the theoretical equivalent of each height of each of those plates, and the height is like this would be equivalent to, say, this dimension, right? Can actually be calculated quite easily. We'll talk about that. And L, the other parameter in this simple formula, is simply the column length. And so we know for your column that this column length is 25 centimeters, is that right? Yes? So that's fixed. And so knowing that there's 25 centimeters, knowing that we can determine the number of theoretical plates from the chromatogram, we can easily calculate the height equivalent of each theoretical plate. And these are two parameters, this and they typically scale because this is fixed for a given column. These are two parameters that are directly related to the efficiency of the column to separate analytes, and that's the bottom line. Okay, so let's look at the reality of how this works. So I just picked off today a couple examples of chromatograms for different applications that show like how these chromatograms often may look in the real world. The chromatogram that you've seen for the 5 anion standard is pretty simple. The chromatogram you'll start to see today for the unknown sample is also relatively simple because of the source of the samples. They're, I think for the most part, they're groundwater samples from the Monterey Bay area. But chromatography is used in a wide variety of applications, and some of which become quite complicated in their need to separate analytes. And so in this top example of a chromatogram, it's showing, this is HPLC, this is showing the separation of 8 herbicides and their degradation products in a standard. And you can see by looking at this, and this is retention time as always on the x-axis and the response on the y-axis, you can see here that many of these peaks come out very, very close to one another. Some of them are sort of masked by other very large peaks, and it becomes very challenging to sometimes separate them sufficiently to actually identify them. There are many labs within the United States, commercial labs, whose main bread and butter is to analyze environmental samples for pesticides and herbicides like this. And their ability to identify them and quantify them, of course, is very important because there's many environmental regulations and policies that depend upon either foodstuffs or environmental samples being below certain threshold levels of known pesticide or herbicide contaminant levels. On the bottom is shown the chromatogram. I think this is also HPLC, reverse phase HPLC. In this case, they're looking at these trimethylsialated extracts from marijuana seeds. And so you can see in this chromatogram that this is, in some ways, for this example, this is an example of a relatively successful separation in your eyes. But you can see there's aspects of it that are really suboptimal. Like that, and certainly like this. And this is quite common. Right? And so as an analyst, you would say, all right, somebody sent me these cannabis seeds, and I want to look at these compounds in there to try to characterize some aspect of these seeds for whatever. And now in my ability to separate these and actually identify and quantify, some of these I feel I can do it quite comfortably. But some other ones, like this, you cannot quantify this because you cannot define where this peak area, the shape of this stops, and these peaks contribute to that. And clearly this whole mess here contains at least 1, 2, 3, 4, probably 5 different things. At least 4 different things. And some of which they can try to identify based on retention time, but other ones they cannot. And so this is quite common, that kind of a challenge. In the field of biological sciences and biomedical sciences, it oftentimes is important to measure different biological compounds. And the top is a chromatogram. In this case, it's a different kind of column that's used to separate this, but it's a chromatogram of nucleotides. And so you have guanidine, dinucleotide phosphate, mono nucleotide phosphate, NADPH, NAD. These are all common nucleotides within a cell extract that people would utilize to evaluate sort of the energetic status of a cell or a tissue. In this case, they're using a relatively new technique called electrostatic repulsion hydrophilic interaction chromatography. And what this is, it all boils down to, in that example, is when you have a column and you have the stationary phase and you have the mobile phase, then you are essentially looking at the chemistry of your compounds that you want to separate, and you're selecting stationary phase and mobile phase compositions to facilitate some type of interaction between mobile phase and stationary phase. And in this case, they're actually using a stationary phase that's electrostatically charged with the same charge as the compounds they want to separate. So in all these cases, these are negatively charged compounds, net negatively charged compounds, nucleotides, and they have a stationary phase that's also negatively charged. And so they get electrostatic repulsion going on. So you think, well, how can they separate things if they're going to be electrostatically repelling each other between the stationary and mobile phase? And what they do is they use a very nonpolar solvent, and mixing nonpolar solvent that's is, well, I'll just say mostly nonpolar, and now you have this sort of battle between the hydrophobic nature of the solvent, negatively charged compounds, and so those negatively charged compounds don't want to be in that hydrophobic solvent. They want to partition in some hydrophilic phase, but the hydrophilic phase, the stationary phase, is negatively charged. And so it's this sort of balance of which one do they hate less, you know? And it forces some of those compounds that may be a little bit more charged, but the electrostatic repulsion is less than the hydrophilic repulsion interactions. And it's facilitated in the separation of these compounds. So there are hundreds of different combinations of things like that to facilitate these kinds of separations. And the last example is looking at a reverse phase. A reverse phase is a form we'll talk about where a column, a stationary phase is a C18, typically meaning a carbon, 18-chain carbon compound or 8-chain carbon chain compound. So it's very hydrophobic. And the compounds that are being separated are all biological compounds that have some hydrophilic character, like most biological compounds. And the mobile phase is typically a polar mobile phase. And so they're facilitating the hydrophobic interaction between the compound and the hydrophobic nature of the stationary phase versus the partition in the polar mobile phase to facilitate those separations. So there's many examples. We'll talk about some of these. In this case, they're separating these neurotransmitters and amino acids. Glutamate is a very important amino acid, of course. GABA is a derivative amino acid. It's a very important inhibitory neurotransmitter. Glycine, of course, amino acid. And you can see even in this case, and in this experiment, they did some drug treatment. They're looking in these brain tissue or cells, cell culture, but they're looking for the change in these amino acids over time. And you can see even in quantifying glycine, glycine's sitting on the shoulder of some other small peak here that's not identified, right? So it's not optimal. And what they chose to do to quantify the glycine here is to draw that other peak here from the baseline and say the glycine baseline should look like this as opposed to looking like that, right? And that's a decision they made. Some may or may not agree. So there's a lot of different combinations of approaches one can use depending on what the goal is. And in all these approaches, in evaluating these separations and the resolution of the separation of these peaks, understanding the performance of the column under the conditions the mobile phase is being used can be quantified by calculating plate height, number of theoretical points. And that's why something of value to understand. Okay, so how do we do that, right? So a lot of information can be derived from the chromatogram you generate, right? And I made a point in both lab sections where I came by saying every chromatogram you generate needs to be saved because you need that because having data separate from chromatogram is it's not useless, but it's very uninformative. So chromatograms tell you a lot about the success of the separation, and there's a lot of information you can derive from chromatogram. And one of those pieces of information is simply to determine parameters related to the theoretical plates. So in this stylized chromatogram, this is from your book, what it's showing is something that we want to make sure we understand, and that is that the plate theory of chromatographic separations has the assumption, an underlying assumption, that the shape of the peaks that elute will follow a Gaussian distribution, right, or a bell-shaped curve kind of distribution. And what that essentially is describing is just the number of molecules, the number of analyte molecules that are sort of hitting the detector at a given time as a function of the elution of the sample in the mobile phase. So in this case, they're showing the number of molecules on one axis, and they're showing the length, the distance migrated, which in this case, they're referring to it as a physical distance, like centimeters, because we know, and we'll see this, that we can easily interchange a length distance here, because we know the length of the column, or we can interchange a time there, because we know how long it takes for peaks to get resolved, right? And we're using a constant flow rate. That's chromatography is almost always conducted with a constant flow rate. So we can quite easily interchange the distance, the velocity of the distance, or time, because we know both the column length and how much time do we loop. So in this case, they're just illustrating to say that when you get a peak that's eluted at a given place, time after going through the column, which is what this is supposed to represent, then it follows a Gaussian distribution of the curve. And by following the Gaussian distribution, we know that there are certain parameters that help define that peak. And in any kind of Gaussian distribution, there's of course the middle that in our case we call this the retention time, right? Where the maximum peak height, the time which the maximum peak height is, right? And then the distribution of the number of molecules, following that example, or the signal, if it's looking at conductance for your instrument, the distribution about that, the middle of that peak, can be described as a term of variance, or a standard deviation. And we know that 1 sigma, plus or minus 1 sigma on either side is going to describe 66% of the observed molecules or signal associated with that peak. And then if we went plus or minus 2 sigma, that's going to be equivalent to 95% of the observation. This is just a fundamental, when you have a bell-shaped curve, a fundamental aspect of the Gaussian distribution is that you can describe and account for either 66% or 95%, or if it was 3 sigma, 99% of the response with that many standard deviation units away from the median response. So this is all now coming down to saying what we want to be aware of is what the shape of the peak is. Right? And we're going to be now looking at the shape of the peak and what the unit, essentially the width of the peak is, either at the baseline or the width of the peak is at half the peak height. Those are the 2 parameters that we can easily determine from the chromatograph that we're going to use. So if we look at a figure like this, and we get back to the simple formula for calculating the theoretical height of a plate, okay, for the height of a theoretical plate, and just going to be a function of the length of the column and the number of theoretical plates in that column, right? So we know L is fixed, that's the length of the column, 25 centimeters, right? We can easily calculate then the number of theoretical plates from this simple formula. And this simple formula gives us 2 parameters that we have to derive or obtain from our chromatogram. One is the retention time, which we know about, that's quite easy. And the other is, in this case, the width of the peak at half peak height. There's several formulas, I'll show you another one in a second, for calculating the theoretical plate height. This is probably the simplest and the most accurate. And this asks that we know this peak width at half the height. And so W sub 1/2 refers to how wide is it at half the height. So I estimated what the half the height was, let's say it's right here, and then I would just measure the width of that in the units of time. So in this case, the width would be, a certain number of minutes. So I can easily determine that with a ruler for my chromatogram, which you'll probably do. Now there's different ways we can calculate the theoretical number of the number of theoretical plates. Like I just mentioned, one formula has us using the retention time and the width of the peak at the baseline, right? And the other one, which I just showed you, has us using the width of the peak at half peak height, at half the maximum peak height. Which one would you imagine would be a little bit more accurate if you were going to be calculating this? You can do it either way. Think the one with the half peak height? You can do either one. You can either measure that or you can measure that. Which one is more accurate to measure? At the half. Why?
Because it depends on how steep it is, I guess. How tall the max would be.
Okay,
No,
no.
if they're on bases.
Usually it's because you never know what this looks like. So here they're saying, I'm going to, and you can see what they do in this figure, I'm going to essentially extrapolate the slope of that peak to where it hits the baseline. I'm going to call that, where it hits the baseline, my width at the baseline. Because I have this sort of asymptoting function with a curve, with a peak comes down and meets the baseline like this. And some people might say maybe it should be here, not there. Sometimes you get peaks that come down and might go like this. And then you say, where do I go? How do I model that? And so estimating where the peak actually returns to baseline is actually sometimes very challenging. And the reason that they modify this formula and have the measurement being taken at half the peak height is because here it's quite easy. You know the peak height is given, for your instrument, the peak height is given is one of the data outputs, right? And then if the peak height is given when the data outputs, all you have to do is calculate half of that value and then go over from the y-axis to half that value and measure quite easily on that chromatogram what that width is in units of time. So it's quite easy to determine. So then you can say, well, now I can calculate the number of theoretical plates from my chromatogram. I know the length of my column, and with those two parameters, I can easily calculate the plate height. And you'll notice on the data printout below the chromatogram that it calculates and gives you the plate height. It gives you h, right? But I want you to calculate h from the chromatogram and compare it with the value that it gives you. Because you might ask, how can it know that? How does the software know that, right? For each peak. And you'd say, well, I guess the software has to know somewhere somebody had to type in that the column length is 25 centimeters. And to be honest with you, I don't know if that's been done. For all I know, there's a default value in there of 15 centimeters, right? Well, maybe each value is wrong. That's something you can check, right? So I would calculate for a couple different peaks what you get for the theoretical plate height and compare that to what the software tells you. And then we can actually find out, is there somewhere that in the software where the value needs to be, for the column needs to be changed. Okay. So I can reiterate this. The reason this is an important parameter and the reason it is a default printout for the data and what it gives you for the chromatogram is because understanding what the theoretical plate height is under your separation scheme is a very important parameter for evaluating and allowing you to compare the efficiency from one scheme to another. And what that might mean is you say, I'm going to run an unknown sample. And when I run my unknown sample, I don't get very good separation of a couple peaks, and I don't know what they are. And I need to separate them adequately so that I can then start trying to determine their identity. And so if the first chromatogram comes out and they're sort of like this, and you know you have two peaks there, then the first thing you can do is say, well, I don't have any money, so I can't buy a new column. So maybe I'm going to change some of the parameters of my mobile phase. That's the only thing I have control over. Maybe I'll change the pH. Maybe I'll change dynamic strength. Maybe I'll go from a bicarbonate buffer to an acetate buffer system. There's a number of things you might do after you look at the literature to see what other people have done to try to resolve those better. And then you'll take from the chromatogram where you didn't get very good resolution, and you can actually try to estimate from these peaks what the, which would be difficult, but estimate from these peaks what the theoretical plate height is and the theoretical number of theoretical plates. And then when you modify your mobile phase composition, and maybe you get a little bit better separation, you can recalculate that, and you would have, in principle, you would have a greater number of theoretical plates and a smaller theoretical plate height that would be associated with that greater separation. And then so that when you published it, you would be able to say, under these conditions, I got a theoretical plate height and a number of theoretical plates for this column size of this. And somebody could look at that and use that from which to build upon to modify that method or do something, or to compare a method that they're developing. So there are parameters that people actually use in comparison of separations. All right. So plate theory, while it's quite helpful to understand this theoretical construct of how these separations are occurring, there are a number of problems with it. It doesn't quite describe all the kinds of processes that are actually occurring within a column that affect separation. Right? It does assume that the partition coefficient is independent of the concentration of the analyte. And we talked early on saying that we assume that's the case in our separations. We assume that the concentration of the analytes from one sample to another, from the standards to one standard to a higher standard, that the partitioning coefficient of the analyte in those standards and samples is independent of the concentration. Obviously, we can violate that assumption if we had too high of concentrations, for example, of analytes in this solution. And we can also imagine that if the partitioning coefficient of our analyte was changing as a function of the concentration, we have a really hard time predicting our ability to separate things reliably across different samples, because it would be chromatographing at different rates and comparing to different places in the chromatogram, only to because they're different concentrations reflecting their partition, right? And remember, how is it you're identifying your compound? The analytes in your solution, how are you identifying those?
The times.
The retention time, right? They don't come out and say, I'm fluoride, I'm chloride. You are using the retention time of the standard to identify this is who it is. And if they don't elute at a given retention time that matches what your standards do, you don't know what they are. And you would conclude that it's something different. And if things are partitioning different as a function of concentration, what that means is they elute at different times depending on the concentration. And you'd be like, I've got different things in here when in fact they're not. So the fact that things are partitioning independent of concentration is a fundamentally important assumption. And that occurs here for the most part. Things that do not occur typically in the columns is that the plate theory assumes that the equilibration is almost instantaneous. That means that the rate at which, when you have a column and you have stationary phase and you have mobile phase, the rate at which that your analyte is partitioned onto the stationary phase and back into the mobile phase is instantaneous. There's no kinetic limitation to that. That's not true. It assumes that the plate theory assumes there's no diffusion, no longitudinal diffusion of your analytes as the analytes are being separated to transit the column. And what that means is as the mobile phase is passing down the column with your analyte in it, you have, of course, a concentration gradient of analyte in the mobile phase. And that concentration gradient is driving diffusion from an area of higher concentration, the sample has now transited, to areas of lower concentrations, diffusing longitudinally in the column, both this way and that way. And if you get longitudinal diffusion in the column, what does that do to your peak shape? It broadens, which is not good, right? Because broad peaks have a chance of then overlapping with other peaks that are identical, right? And then the separation is small. So plate theory doesn't necessarily account for that. It doesn't account for the fact that there's other kinds of interactions going on between the analyte or processes going on within the mobile phase that affect your analyte. That may vary as a function of how fast the mobile phase, the flow rate is going through the column. If you are pumping it really fast, then you're sometimes likely to get small non-laminar eddies, laminar flow eddies that form around the stationary phase particles. And those eddies can affect how long an analyte will stay sort of trapped in that versus transiting down the column. And if it's going really slow, then you can have sort of what's considered a stagnant layer around the stationary phase, where the concentration gets depleted because of partitioning, and it affects the separation of the rate just the rate of separation. So those are the main problems with the plate theories. It doesn't really account for all those things, which actually are important in affecting separations. And so this has led to sort of a modification of how we think of the theory, the processes that are affecting separations of analytes in chromatographic column. And they term this sort of revised conceptualization of these processes a rate theory as opposed to a plate theory. Okay? And so the rate theory still sort of builds on the idea that there are hypothetical functional units in the column upon which analytes are partitioning. But it incorporates other kinds of physical processes that occur in the column to describe that separation more realistically. Okay? And these are that. So when we consider the rate theory, the advantage over plate theory, one is that it allows for the reality that the peak shape is affected by flow rate, right? And we know that, and you'll see that. When you start doing your Van Deemter plot exercise for the lab, you'll see that the shape of the chromatographic peak that you're eluting will change as a function of the flow rate of the mobile phase. And that makes sense, right? When you think of it conceptually, it makes sense that the peak shape will change for a given injection of a given amount. The peak shape changes as a function of how fast the mobile phase is. And this rate theory allows for that recognition of that phenomenon. It also allows recognition of the phenomenon that in a column, that you can have analytes that are transiting the column in the mobile phase and partitioning on and off of the stationary phase, that they can follow different paths through that column. And those paths are not all the same length, because you have a lot of stationary phase feeds in there, and some molecules are going like this with the mobile phase, some may be transiting with maybe a more direct path, and so the path length that mobile phase, I'm sorry, the path length that analytes are following in the mobile phase may differ slightly for one analyte molecule compared to another. And that was not accounted for, that phenomenon is not accounted for in plate theory, but it is agreed. So when we think about how it's modified, what we end up with in a rate theory construct is looking at the theoretical plate height, which is the parameter that we are quantifying our column performance with. And we are looking at these different kinds of processes that may be affecting our determination of what that theoretical plate height is. And they include a longitudinal diffusion component, I just talked about. They include the fact that there are mass transfer, differences in mass transfer rates of analyte onto the stationary phase and back into the mobile phase. And it accounts for, there could be diffusions associated with the mobile phase that could be affected by eddies and things like that. And so they can put this together in this overall term that has different components that reflect the longitudinal and mass transfer contributions to how analytes are behaving in the mobile phase during separation. So let's look at each of these terms individually. So when we look at those kinds of processes, I didn't mention this, but in reality, in chromatographic separations, a contribution from having a stagnant layer of mobile phase around the stationary phase is typically negligible. The contribution of having that stagnant layer in terms of affecting the chromatographic performance of separation is typically negligible because the flow rates are sufficiently high to avoid or minimize the formation of these stagnant layers. If you had an extremely slow flow rate, then that would may not be very practical to use. Then you could have a potential contribution of having mobile phase around particles of stationary phase that became stagnant, meaning were depleted of analyte, for example, and were not mixing with mobile phase, it was transient. But in reality, that doesn't happen. So this term would typically be ignored. So if we ignore that and then look at the other terms that help describe the separation process and the plate height construct, we can actually rearrange this, and they have rearranged this into something that's actually a determinable equation that's been termed the Van Deemter equation. And in the Van Deemter equation, we are then being mindful of these processes that are important that affect the separation efficiency. We're still looking at the theoretical plate height calculation to determine. And now we're looking at a number of coefficients that describe these processes. And so for A is the eddy diffusion coefficient, B accounts for this longitudinal diffusion, and C accounts for this mass transfer kinetics. And this is something that we know, the mu is just the mobile phase velocity. That's what it's always been when we're talking about these kinds of equations. So the Van Deemter equation now is the equation that's used to replace the plate theory construct that allows us now to say I can account for these different processes in the column that affect my theoretical plate height that I can calculate. And my theoretical plate height is directly related to the chromatographic separation efficiency. So now, by using this construct, I can say, I can connect how efficiently I can separate different analyte peaks with a theoretical construct that puts me together that allows me to understand what may be happening within the column described by this. So we can look at the first term, which is the longitudinal diffusion coefficient or process, the Van Deemter equation. And this shows this cartoon 3 different time periods of the separation. And in this we have analyte molecules, which are supposed to be the big donut circles, and then the stationary phase are the little X's in this column. And we're looking at the variance in the length. And so here we have L looking at the length of the column. It's the parameter that is being shown. And sigma is the variance in that length, meaning how spread out are the analyte molecules across the length of the column as it's being separated along the column. And so you'd say, at time 0, when I load my sample onto a column, all the analyte molecules are as close together as they can, because I've loaded as a discrete sample. At that point in time, there's no, the variance of that, meaning how spread apart those molecules are, is 0, right? Then after some point in time, before I get the resolution time before the peak actually resolves, I'm starting to get some broadening of the peak as those molecules are diffusing as they're transiting down the column. So they're transiting down the column, but also diffusing out this way. And that results in a broader peak. And then by the time the peak actually resolves and hits the detector, I get somewhat of a broader peak. And I can describe that diffusional process that contributes to peak broadening, right, which is something I want to minimize. I can describe that by considering a longitudinal diffusion coefficient, okay, and also the time it takes to resolve the sample in the normal phase. And so the variability, the variance in how those molecules spread out in length in the column is going to be a function of the diffusion coefficient in the mobile phase and the time it takes for the sample to elute in the mobile phase. And so all I'm considering here now is like, all right, if I know that diffusion coefficient, which is going to be affected by the chemical properties of the analyte, as well as the chemical properties of the mobile phase, if I can empirically determine this diffusion coefficient, which people do, and I know how long it takes for the peak to elute, then I can actually estimate what the contribution of longitudinal diffusion has had in the separation process. And I can quantify that. People who do column chromatography, development of columns for column chromatography actually do that. The next term of the Van Dienberg equation, which is the mass transfer in and out of the stationary phase, it accounts for that process of essentially partitioning on the stationary phase, partitioning off the stationary phase, it's shown there. And it's a function of that mass transfer partitioning coefficient, C, and the mobile phase velocity units, as simple as that. And here we can look at this cartoon to say, if I have now essentially the dividing line between my stationary and my mobile phase, which is the solid line going across. And I have at the top my mobile phase fraction, and I have on the bottom of that line underneath the stationary fraction. I can see that at time 0, when I put them in, there's some instantaneous interaction between both of those, and they're essentially, the same place in the column. As the mobile phase is going through the column, over time of elution, I can see that as things are partitioning onto my stationary phase, the molecules that are in the mobile phase keep moving. And the ones in the stationary phase are sort of arrested in time for a small amount of time while they're partitioned in the stationary phase. And so the mobile phase molecules are moving past those, the stationary ones are stuck. The longer the elution takes, even the longer the retention time, the farther spread out those become. And so that when they finally elute out of the column, now I have these two groups that elute out of the detector like a band like this, as opposed to a more concentrated band of analyte molecules at the beginning. And that contributes to peak broadening as well. So now I have these two processes, a longitudinal diffusion and the contribution of mass transfer kinetics, the rate at which things are partitioned on and off of the stationary phase, that are both contributing to the broadening effect. And in chromatography, fat broad peaks are usually extremely suboptimal because there's a higher likelihood that we may have overlapping. So this eddy diffusion that you can have, I talked about a little bit, which is described by this third coefficient in the Van Dienberg equation, and I sort of drew that. This is just really taking into account the reality that the linear path through a column, because of the packed in the stationary phase, is not the same for all analyte molecules. And some will find maybe a shorter path when they're eluted, and some will find a longer path when they're eluted. Of course, these that find a longer path will get retained in the column longer, and those that find a shorter path will have to retain in the column less time. And in both cases, that contributes to a broadening of the peak. The ones that come out sooner found the shorter path. The ones that come out longer have the longer path, right? So those are three things that actually happen in the column that could be accounted for in the Van Dienberg equation that actually explain the separation process. So what does that lead us? That leads us to this question of, all right, I think I understand now, if I think about it a little bit more, some of the processes that are actually occurring within a chromatographic separation. And now I have the chore of trying to say, how am I going to set parameters when I'm designing a separation method in order to optimize my separation. So this is what we know. You have some analyte, say there's some sample has a couple analytes in it that that when you have a relatively fast mobile phase velocity, let's say 1.5 milliliters per minute, you might get something where they come out, and the other one, and it's not quite resolved, the other one comes out like this, right? Maybe this is, right here is 15 minutes. Okay? And you say this is 1.5 mils per minute of my mobile phase velocity. And I say, I'm not happy with that. So what do I do? So now you have to make a choice. What do I do when I see this? What might I do?
Change the velocity of the voltage.
Okay, so you say, would I increase it or decrease it?